beyond that, up into higher level environments. And when we first thought about going into Java, going into Ruby, going into Python, we have to go instrument dynamically all these interpreters. We have to instrument the bytecode dynamically. And Adam developed the statically defined tracing provider for username, USDT. And we discovered with USDT, you can actually do a lot. If you just went into the interpreter and said, here's where I'm calling a function, here's where I'm calling a method, here's where I'm loading a class.
Incredible occurrence too. Actually, Jared discovered this. You know, so we had discovered we had written USDT basically just for block staff. And we thought, oh, we'll figure out something else to do with it later. And Jared came back and had identified all these JVMTI, all these instrumentation programs in Java. So like, what if we put a probe there and had like the Java provider hacked up in like 1,000 lines of just awful code, frankly, Jared?
No, it was pretty. I can give you the full story from full story, real quick.
Okay, real quick.
So this was at it was a meeting with Sun executives, customers and Sun executives, and everybody that was there, all the customers said one of the things we really hate is no dtrace for Java. And so Schwartz asked the guy that was there that's responsible for Java at the time, who I was for the people inside of Sun, his initials are JJ as well. And he said it's an extremely hard problem to solve, and it's going to take 2 years before we can solve it. And so we went out for dinner, drinks, lots of drinks. And then I went back to the hotel and said, you know what, I don't think so. And so I coded it in about 4 hours. After a lot of drinks. Hence the ball repeat. Hence the coding style. And then the next day I was supposed to do a dtrace demo for everyone. And so I did a dtrace demo of DVM. And the person who said it would be very hard got no end of shit for this setup.
So unfortunately, it did nothing. It didn't hurt his career at all. But but I think what was interesting about it is that you had taken what was, I think all of us were thinking like, I guess that's kind of a naive approach, just going up instrumenting these kind of, and like passing in char stars and userland. But all of a sudden we realized this was actually incredibly powerful because there was nothing there before, and you could shine this ability for it light. And then the next major step was these enable probes, where we were able to put bodies of code, and just say, if this probe is enabled, execute all this body of code. And it was, kudos to the Ruby guys for finally giving us religion on this, because the getting the Ruby class name, method name that's executing, it's like getting a bill through Congress. I mean, it's ridiculous. I don't know what that is. We had to go to this enable probe. But we've gone, this course has carried us really far. I'm going to be interested in this session to see if this course will carry us still further. And I'm especially excited by Erlang, which is a really interesting environment. I know it's not a new environment, but I think it is newly popular because of what it can do for currency. So with that, take it away.
Thank you. Quick thank you to everybody. My co-worker on this project is Tim Becker. We started at Christmas. Tim is currently deep into learning about smart cards. And I've been dealing with all kinds of other stuff. So I apologize if it's not that fabulous, but it's much more fabulous than it was in February. Also, thanks to Team dtrace for getting us onto the OpenSolaris.org, because we didn't have anywhere to host the code. This is not an official Ericsson thing. Classic presentation. I'm going to tell you what I'm going to tell you. I'm going to tell you again. And I put the demo at the end in order to make you listen. Okay, so my view is very much a user-land view that what I want to be able to do is dtrace end-to-end. And of course, because I'm a new zealot convert to Erlang, what I really want to do is use Erlang end-to-end with kind of, some user interface, like Firefox or something. Because Erlang provides a fully distributed, clustered database of its own. It provides its own highly concurrent, really hard to bring to its knees web server, and it's got everything pretty much that J2EE has out of the packet, and it's free and it's open source. Like, why would you not have it? So I'm going to be able to.
That's why.
Sorry?
Is it log? That's why you would.
Absolutely, there are syntax issues. There are syntax issues. But I would like to be able to trace all the way through that guide and be able to answer very concrete questions from a use case of the user perspective. That's my view of what I want to be able to do. So that's general scope. For V1, of course, what I really want to be able to do is what Erlang is about, which is clustered distributed systems. And I'd like to be able to pull this all together across a fault-tolerant cluster, which is where Erlang is actually beneficial over more traditional ways of building these systems. So this is version 1 of the dream. Version 2 is many, many machines. The Ericsson people tell me that the typical cluster is in the 10 to 100 machine range, and typically you have small dozens of virtual machines on each machine. Okay? And that's what pretty much runs the telecom backbone of the UK. So Erlang is in pretty much every non-local telephone call that you could make in the UK. And that's a reasonable footprint. Its claim to fame is really this 9 nines of availability, which is 1 second in 31 years. And that's purely based on real production systems in telephone switches. The real beauty of this thing is it's a portable VM, and the language itself has fault tolerance support built into it. And that is part of what gives you those 9 nines. Another part of it is you can dynamically load code. You can have 2 versions of the same module of code running simultaneously, and that's not a problem for those VMs. Okay? So we've got some very nice capabilities to build big fault-tolerant systems, and as you probably know, people like Amazon are using it. The second thing about Erlang, which is pretty much the thing that everybody hates when they come to it, and I was one of those people, is it's a very ugly syntax functional programming language with some weird shit in it. When we say first-class functions, we kind of all have this mental model of lambdas. And what the really nice thing about Erlang is, you can send that as a message to a different node somewhere else running on a different architecture, and it will arrive and be executable. So these are, very anonymous. There's pattern matching as part of the functional syntax, and so instead of thinking of overloaded functions, you have pattern matching, and at runtime the guy figures out which particular implementation you want, and we've got dynamic types. So it's not like Haskell. So if you're a SML or a Haskell person, this looks different. This looks much more like Lisp or Scheme with loads of syntax instead of just parentheses. It's got very fine-grained concurrency. Process, an Erlang process, and I'll use the word process a lot and confuse everybody, because what I mean is an Erlang process, it's less than 250 bytes. And so it's pretty easy to run 100,000 processes on my laptop. That's no problem at all. And it's pretty easy to run several VMs, each with a few 100,000 processes on. It's a very standard paradigm of creating these models of highly concurrent systems. Again, the Ericsson people say about 6 Erlang processes just for a telephone call. To monitor the call, to charge the call, to make sure the call got through, to break down the call, figure out who to actually allocate this to. It has an asynchronous, anonymous messaging system. So when I send a message to somebody, I know who I'm sending it to, but they don't know who gets it. And that makes correlation of events across an Erlang system quite hard. So I'm really saying all of these things because I just want you guys to walk up to me and say, Gary, that's trivial. You just do it like this. Okay? So this is really my basic picture. So inside the VM, we have, and the Erlang terminology is a node, we have paths of data which happen to be modules, which is the unit of code loading, with functions in. It's not an object-oriented language. We just have this flat module namespace, and inside we have functions, and we can use this pattern matching syntax. So this one says, call this function if you happen to have in your hand as its only parameter a less than. This second piece of syntax says, no, use this one, same function name, but use this one if it happens to be a list that has at least a head. The body may be empty, but the head of the list is there. And this funny square bracket bar square bracket syntax is exactly a pattern match for a list with a non-null head. So that's what the Erlang code looks like. And sitting next to that in there are many, many, many of these teeny processes. As a general rule of thumb, there is no shared state between processes. And hence the reason that you can have lots of them, and hence the reason that you adopt a very different style of programming from maybe one that you're used to. Sitting across the bottom of all of this, of course, is a big sub-basement full of C code. And our initial attack on this whole problem of how do we put dtrace in is, of course, to start at the easy place, which is the C code. And the C code comes in two basic flavors. There's stuff which looks to the programmer like built-in functions, which are called ifs. And this looks exactly from the outside like any other Erlang function, down to the pattern matching mechanism. And there is a little bit of global state that is manipulated through functions. And think of it like a baby registry. We've got to be able to get to processes, and therefore we have a registry mechanism. On the other side, we've got a whole pile of mechanisms. There's this dynamic code update, which sucks one or more, some subset of modules in, hooks them in so that new processes and new calls will run through it. There's all of the process management stuff, spawning and scheduling. Of course, we've got memory allocation. And part of the fault tolerance mechanism is hooked into the messaging mechanism. And so you can say, I want to be in a relationship with a process so that if it dies, I want to know about it, even if that process is somewhere else in the cluster. It's a very uniform syntax. And you'll get a message. It's a special kind of message, and we want to be able to hook that out. Then the last piece is something that sort of sits between these. There is a tracing mechanism inside, and because it's designed to be up and running all the time, we can switch that tracing mechanism on during runtime, during live production. We've got to be careful, and we can siphon bits of information out of the system, and it uses the pattern match syntax. So that's my architecture that we're playing with. What we're doing as our initial scope is stealing the Ruby idea of exposing dtrace into the programming language itself. And so the architecture of the tracer is that we can have a process, an Erlang process, that all tracing information goes to. And we can provide that. So by having a few dtrace facilities surfaced into Erlang, I can write a new trace backend and just trace the entire thing straight into dtrace. It's one piece of the strategy. And then we can use statically defined tracing within those subsystems. And really what we want to be able to do is leverage where we can pieces that are in there and go and instrument whatever we can't get at that way.
So, Gary, sorry, so you're making calls in Erlang that will be effectively dtrace probes?
Yeah.
Okay.
And that my little teeny weeny demo is exactly that.
Cool. And is Chris Andrews is here somewhere, right? Yeah, you're doing the same thing in Ruby, effectively.
Well, I don't know. Are you able to fire arbitrary probes that show up after the process is started, or is it like Ruby where you've got a single probe that you can fire with arbitrary attributes?
The latter.
Right.
And right now it's not even arbitrary attributes. One of the pressures on us is we want to be very efficient. We don't want to put a big pile of overhead on. And some of the Erlang data types are quite inhospitable. So our base data type is list. And the list is a singular list of some arbitrarily large size, all contained within one of these Erlang processes. Strings are lists. And so some of the stuff that we have is very unfortunate. What we do have, though, is a couple of base types. There's an intern string, which in dtrace, in Erlang vocabulary is an atom, exactly like a scheme intern string or Java intern string. And we have binaries, which is exactly the stuff that comes squirting through a socket. And it's a byte sequence. So we've got stuff which is extremely cheap to pass across and pass around between processes. And because it's a single assignment language, we know it isn't going to change underneath us. So we're using that stuff. We also need to be able to understand what process is creating what process. And so in the operating system world, we have a process tree, we have the same sort of thing in Erlang. The majority of Erlang processes are anonymous conceptually, but they get made by something that wasn't. And so we've surfaced that. We're having some struggles in this area about using the trace facility, but I think we can figure that out. But the things that we would really like is some help to correlate messages between all of this, and I need to get some help out of Ericsson to do that, and some way of making Erlang data types be nice, easy dtrace data types. We can absolutely flatten this stuff to strings, but one of the very natural models of using Erlang processes is you comes up a bigger and bigger and bigger list, of state and information that you want to manage. And so, as you go through something, if it's been living for several days, the state could be quite big, and you don't want to smash it down to a string every single time you go through this guide, simply to hand it across to dtrace. It'd be nice to have some operations on the dtrace side to deal with. So in future, and I'll get to the demo pretty quick, we want to use the existing Erlang trace facilities as much as we can. That then raises the issue about how do we talk about bits of Erlang code. We want the dtrace script to be able to say, I want to trace this thing, we want to get that information into the trace mechanism on the Erlang side because we can just switch it on. So we would like that, please. And we would almost certainly like some sort of correlation identifier that we could tie together and maybe push underneath the covers so that we can see stuff swooshing into our Erlang process, OS process, rolling through the VM and then back out again, so that we can do those end-to-end use cases, which is really what I want to do, and get those Erlang data types in. So, let's go and look at my teeny demo. What I'm going to show you is really using Erlang itself a little bit like awk. So if you imagine awk for TCP/IP, what you want to be able to do is stuff a little process in there and see everything that goes flying up and down the sockets, say. Absolutely something you can do with dtrace, but it happens to be that I can write all kinds of stuff in here which I need to do for a job. So that's the basic structure of this tiny demo. And so one of the interesting aspects of this is, I hope, I can show you a little Erlang program. So this is that entire pseudo proxy, okay? There is no fancy stuff in this. There's no fancy framework except for the TCP connection. So you can see this weird looking syntax. And one of the things that stands out is there are no loops. There's no for loops, there's no while loops. The only looping construct, which I called loop to help the reader, don't need to, is that this guy just calls back. And so what's actually happening is, this is tail recursive. And tail recursive things don't need any extra stack space. The compiler can convert that apparently recursive call into a flattened call. And so all of the work is in here. We're getting some message through this receive statement that we have yet to instrument. And we're simply passing it through, and we could do anything that we want in between. So what I'm actually going to do is stick our little Erlang dtrace function, and I'm going to pass that stuff through. And all this guy does is it takes it, exposes it to a dtrace code, and returns that stuff as its own value. So you can poke this in code all over the place without actually breaking the structure of the code. So this is a pretty simple demo, I hope. Now I've already got an XMPP server running, I hope. Let's just see. Now it happens to be that I made it hard for myself by using an Erlang XMPP server called eJabD. And so I'm running a different version of Erlang for that. Let me just bring up my... So I've got a teeny weeny little dtrace script I'll show you in a second, if I can remember my password. And I do the same thing. I like to know that I'm observing Erlang because that seems like a good demo. Now when I press return, I've got this dtrace script. It's watching the Erlang instance that I'm about to start up. And so one of the things that you will see is there's an awful lot of stuff spewing through. That's because Erlang itself, the virtual machine, behaves exactly like an operating system. It pretty much allocates a process to manage anything. So there are